Welcome back. In this tutorial, we are going to create an urban data visualization where I'm going to rely on the Charles University's recently published Urban Morphology Atlas, and then we will see how we can create insightful and colorful maps of Vienna using this categorization. Let's see how this looks like in Python. In this tutorial, we are going to visualize some urban data. Here, the input data source is going to be coming from this website called Urban Taxonomy. You will find the link in the notebook and in the comments and on Substack as well. So this project is a very exciting one. I recently saw this on LinkedIn. It is created by a group at the Charles University in Prague. Here you will find all the credits and also their contact address. And in this project, they combined more than 20 different data sources to build a large data set of buildings and urban areas. Here you will find the data as well, to create a very detailed urban morphology data set. Here you will also find their paper on the archive led by Martin Fleischmann. And if you go to the download part, you will find all the data we will use in this tutorial. Here, if you scroll down, you will also see all the different data components that went into this modeling approach, from global data sets like OpenStreetMap and TomTom, all the way to more than 20 different local data sources. This list also very nicely highlights that if you want to do a good quality analysis across many countries, many cities all over the world, then using global datasets like OSM or TomTom or Sentinel or whatever is usually a pretty good call, because using just one data source, so having a relatively simple data collection and data processing and pre-processing pipeline, we can cover a lot. However, if we want to have really high quality and high detail information at a local scale, at the scale of countries or cities, then we will need to include various local data sources as well. These local sources, of course, don't scale from country to country. However, they provide much deeper and much higher quality details on the level of the country or the city, so it usually worth to include them if we have the resources. It's also a good question how this will evolve in the world of open geospatial. So maybe in a few years there will be one unified platform which will take all of these information together, and there will be no need to stitch together different datasets like this. But for now, this is how we can work our way towards a more detailed analytics. However, here the analytics was already done, so we just have to go to this website and download what we want to visualize and what we want to study. Here, as an example, I will download data from Austria, from the 81 NUTS region. Here, you just have to click on the link. We will go for the building dataset, where, as you will see, we will have building polygons and morphology class labels. These labels will be integer numbers, so we will need to go for the common files and find the mapping which stores the names of these label numbers. So after downloading these two files, this one is a small JSON, but the other one is a fairly large GeoParquet. So once you have downloaded them, you can go to the Python terminal. Once the downloading is done, we are back to the Jupyter notebook. First, I just add the link as promised, urbantaxonomy.org. And then I will do the usual imports. The OS library to read and create new folders, matplotlib to visualize things, OSMNX to get data from OpenStreetMap, pandas and geopandas to work with tabular data and tabular data with geometries, Shapely to create geometries from scratch, the patches library from matplotlib to customize figure legends, regular expressions, and a JSON reader. After the import, let's just call this section data parsing, where first I will download the admin polygon for the target area. So now we will focus on Vienna, for which now I will query its boundaries from OpenStreetMap and quickly visualize it. The reason I picked the NUTS region 81 is because that's where Vienna is located. Then let's read the Parquet file, and also once we read it with pandas, print the number of rows it has and have a sneak peek of the data frame as well. It might take a few seconds to parse this file because, as you see here, it has more than 1.5 million rows, which means about 1.5 million building footprint polygons across Austria in this specific NUTS1 region. So here you see that we have a geometry column. However, if we try to query one element, you will see that this is actually stored as an array, so it's not yet a polygon. So now we will have to turn this into a polygon object using Shapely, and then turn this data frame into a GeoPandas geodata frame. For that, first we will need to define a helper function. This function takes a geometry as in an object from the geometry column of the input data frame, so an array of coordinate dictionaries, from which we will extract all the relevant coordinates, turn them into a list of coordinate pairs, and then use the polygon constructor of Shapely to turn that into a polygon. Then all we have to do is to apply the parse geometry function on the input geometry column, and then see how this will turn these arrays of lists of dictionaries, if I'm right, into proper polygons. Again, we are running this function over 1.5 million records, so it might take a few seconds. But once it's done, we can also query and output just one single element from the geometry list. And as you will see, now we have a decent Shapely polygon here. The next step is to turn this data frame into a GeoPandas data frame. So here, I will take the geodata frame constructor from GeoPandas, feed the df data frame as an input, specify the column where the geometry information is stored, and also the CRS. So if you go back up here, you will see that these numbers are in the scale of several hundred thousands, or no, in the scale of a few million. And after some digging, turns out that this is most likely to be stored in the EPSG 3035, which is a fairly standard projection system in Europe. But then, to make sure it aligns well with what we have in OpenStreetMap, we will also turn this into the usual lat-long projection. And since this dataset is quite large and we will only want to focus on Vienna, let's do a quick overlay where we will crop this data frame to its subset falling within the boundaries of Vienna. Here I will only take the geometry column because, as you can quickly check, any dataset or data frame created from OSM has loads of other columns and other information which we don't need. We just need the admin boundaries, the geometry of Vienna, to use it as a mask. And after this step, I promised it's gonna get faster because we will have a much smaller dataset. And while the cropping and the overlay is still running, let's start to prepare a simple visualization. Also, one note, if you want to speed this up, one way it will need you to write a bit more code would be to create a new geometry column or even a new geodata frame where you turn every footprint into its centroid, and then you can do a spatial join between the admin polygon and the centroid point coordinates, point geometries, much faster. But for now, this was fine for me. I could have a sip of tea or coffee in the meantime. So now, as you can see, from 1.6 million, we arrived to about 250,000 footprints, which is a lot more manageable. But to quickly visualize it, we will need even less than that. So I will take a sample of 10,000 records from this data frame, specify the axis, and set a fairly visible red edge line for the building footprints. Also, to make sure that we see where Vienna is, we plot the admin boundaries on the same axis. We are not using any fill color, and we will use a thick black boundary line. And now here we have confirmed that we have Vienna here, and also we have loads of tiny things in it, which are probably the building footprints. We can double check that by very simply plotting one sample. And yeah, this looks like a building footprint, and this looks like a building footprint, and this as well. We could sample two as well, but there is no guarantee they will fit on the screen very nicely. So just drop this for now. And we are still in the data parsing part and data cleaning and pre-processing part. So let's see what we have here. So now we have a restricted data set only covering Vienna, where we have the IDs. These are pretty much the building IDs. And we have the labels as integer numbers. So here are the label columns, the bounding box, and the geometry. So next, we will need to turn these label ID integers into something that's human readable, for which we will load the label name JSON and turn it into a dictionary. So this is a dictionary of dictionaries where you will see the hierarchical layers of the morphology classes. Then we will need to iterate through the primary hierarchy layers 1, 2, and 3, which I will do here in this short Python loop. And after iterating through each of them, we will create new columns for every level, a column called name. And if you run this, you will see that in the first level, we will have two classes, Incoherent and Coherent fabric. And then if we move on to level 2 and 3, which is where we stop here today, we will have 4 and then 8 different classes. Since the human eye is usually good at differentiating about 7 colors, having 8 categorical labels and then coloring them with different colors on the maps will be fine. So now I think that we are on the right track. We can also quickly count the number of unique values. I just happen to remember it from the time I prepared this notebook. So here you can see that we have 2, 4, and 8 unique values in the different levels. So now we can move on to the visual part, where I've been thinking about what to visualize and how. And since the original website had these nice circular maps at the scale of about 5 to 20 kilometers, I thought that I will do something similar, just in a bit smaller scale, so it will fit the urban topic better. First, let's develop a pilot visualization. First, I pick a location from Vienna. It's a center one. And then turn it into the local coordinate system, so making sure it's meters. And for now, this is so for now, this should be just 1 point. Yeah, it's a point with 0 size. Now let's turn it into a circle by buffering this point. So this is going to be the sample area we will visualize. So we will have to use this as a mask to crop the large geodata frame, which first we will need to turn into the local CRS. Once we are done with the CRS reprojection, we will do the cropping and do a very quick plot. So this should already be a footprint dataset restricted to the circle. Yeah. And it looks pretty nice already. You can see this old typical Central European structure, building structure and city center here. But we will get a much nicer map very soon. So for that, let's define the canvas and plot the most detailed categorization and also visualize the circle around it. We might switch it off later on. Yep, so now you can see that the plot aspect is a bit off. So now we don't have a circle, but we have this slightly stretched circle. So for that, we need to switch to the equal aspect stretching option and also switch off the axis. So now it's quite decent already. Then the next bit we will add is a styled title box. So I will copy the code, and I have to admit I fine-tuned all the tiny parameters of this one with ChatGPT. These are the sort of things ChatGPT is pretty good at. So asking to place a text saying Vienna and then slowly positioning it to the right place. So what happens here is that first we define the location and then the text to be displayed. 0.2 means that it's very close to the left edge of the image, and 0.98 means that it's very close to the upper boundary of the image. And here we also specify that it should be aligned to the left and the top, although I'm not sure we need that because it's already defined in these coordinates. Then we can specify the font size and set it to be bold, and we can also color it the way we want. Maybe we can change to dim gray, for example. And then the bounding box, which has now face color white, but if we switch it to red, then you will see that it's actually there. But let's go back to white, which kind of blurs out behind the title, and then we can customize its further parameters. It should be rounded, it should have some padding around the text, and how strong the opacity should be. Then let's add a base map, and then you will see why I wanted to add this box behind the title. I will use the positron no labels base map, so it will have a fairly mild impact on the final visuals, but first we will need to import context.li to get there. Yep, so it's barely visible, but it's a nice final touch. Except this promotion here, we know it's from OpenStreetMap, we know it's from Carto, but we don't need to be reminded every second. So let's add a colored patch, which is actually going to be white. Here we specify the location same way as we did for the title. We make sure it's white and it's on the top layer and it's not transparent at all. And now it's blanked out. We can also set a tight layout now that we are here at the final touches part. And now there is just one thing missing here. It's the legends. So that's going to be a long piece of code because as I've been trying to make this visualization work, turned out it's a bit more tricky than I expected. So first, I will prepare the labels here. So as you can see here, we have 8 different labels, and the trick will be that Some of these have a pretty long name for this visualization, so I had to redefine them in the following order. Then a quick filtering to make sure that we only visualize what we really need to visualize. And then we do a cleanup step. So we will get rid of the fabric word, for example, which is present in all of them, and do some abbreviations. So make sure they are a bit shorter. And then we will also generate new colors. We will add a single unique color to each of these unique labels picked from the tab 10 matplotlib color map. And then we will use those to generate patches, which will look like this. So now we can copy these lines back to the original plot. Probably after here is fine. And then add these legends. So the handles will be the patches we defined here. We will set them to be here below the visualization. We will place them in 2 columns, and that's why I had to organize the labels in a rephrase in this specific order, so they will be nicely aligned, and then a few more parameters to make sure they are well placed. And as you can see here, now we have a reasonable legend box right below the visualization. Once we have these final touches done, we can move on and create a series of visuals. For that, I will simply factor previous batch of codes, all of these, into one single function. And again, this is the usual stuff ChatGPT is really good at. You just throw some mechanical things to it, and it will properly adjust them and turn them into a nicely structured function. You will find this function on Substack, so don't worry if you can't type it in right now. And then a few locations. Make sure I set the title color to be dim gray. And then simply running a loop which iterates over these locations and creates a visualization for each of them and exports the images. The center we just show then a suburban part. Here you see that the coherent interconnected part, which is probably a series of residential houses, gives a much more different picture. Then again, here we have a different picture, and here as well. To wrap it up, this is how we can quickly download and visualize in a nice way this really exciting urban morphology dataset in Python. So I recommend you to test it, try it out, see which countries and which cities are currently available, and create visuals also reusing my code, and let me know how it works. Thanks for following this video through, and see you next time.